Malaysia Airlines Flight 370 disappeared over 11 years ago while on a routine flight from Malaysia to China. For reasons still not known, it diverted and ended up crashing into the southern Indian Ocean. The crash site has still not been located. Recently, there has been considerable excitement over the possibility of using archived amateur radio signals known as WSPR to track MH370 on its flight south. The proposal was originally made by Rob Westphal and has been developed extensively by Richard Godfrey and collaborators. This presentation will examine this work in more detail. As usual, we start by asking ChatGPT, can WSPR be used to track aircraft? The first answer returned is quite positive. However, if you wait a moment and ask again, the answer is quite negative. Clearly, we need something more reliable than ChatGPT. WSPR stands for Weak Signal Propagation Reporter. It was invented by Joe Taylor. It is a one-way beacon system between a transmitter and receiver. The path connecting the two is a link, and a single decoding of a transmission is a spot. Transmissions are made every 2 minutes. Its purpose is to monitor radio propagation conditions worldwide. The primary mechanism is by radio signals bouncing off the ionosphere, often via multiple hops. To avoid interfering with other signals and to avoid cluttering up ham radio bands, the power and bandwidth are kept quite low. The information encoded in the beacon transmission is quite minimal: a call sign, location, transmit power, and message type. A small portion of each amateur radio band is allocated to WSPR signals. The common high-frequency bands are shown here. During any 2-minute interval, dozens of stations around the world are either transmitting or receiving, and sometimes both. The receiving station can upload the decoded information to a database at the website whispernet.org. Anyone can then query the database to get a worldwide view of propagation conditions. Historical data go back to 2008, and as is relevant here, those data are available for the night of March 7, 2014, when MH370 disappeared. The ionosphere actually comprises multiple layers in the upper atmosphere. Radiation from the sun causes the rarefied atmosphere to become partially ionized via various mechanisms. The upper figure shows the relevant layers for both day and night. The amount of ionization is tied to the 11-year sunspot cycle, and radio propagation conditions vary considerably as well. The bottom figures show pictorially how radio signals propagate. A transmitter is located at the bottom left and sends out rays at various elevations. Rays at high elevation pass through the ionosphere and escape to space, but those at low angle can be refracted by a sufficient amount that they return to Earth, where they can be detected by a receiver. Multiple hops between Earth and ionosphere are possible. The figures on this page are a bit complicated, but let me describe them. The top figure is called a waterfall diagram. The horizontal axis is frequency within the WSPR band. The vertical axis is time, which increases in a downward direction. The horizontal white lines mark a 2-minute interval during which a WSPR transmission occurs. You can see signals from 3 different stations. Below are signals from the next 2-minute period. The map shows links for all spots in a single period, and you can see that they span the globe. Here's an example of how one can exploit archival data. Guglielmo Marconi made the first transatlantic communication in December 1901 when, while stationed in St. John's, Newfoundland, he heard the Morse code letter S being sent from a station in Cornwall, England. The exact details of the equipment he used are not known, but the frequency was somewhere at the low end of today's AM broadcast band. What was not known at the time was that he had fortuitously chosen a month and year at the sunspot minimum, which turned out to be optimal. We can't replicate his experiment exactly, since the AM band is filled with broadcast stations and spark gap transmitters have been banned since 1934. However, there are 2 WSPR bands that straddle the AM band at the frequencies indicated. I extracted the archival WSPR data for December 2019, which is also at a sunspot minimum. The figures bottom right show the signal-to-noise ratio for all spots in the database plotted as a function of time of day. Successful spots were all made at night. The gap in the middle corresponds to daylight hours. Curiously, the times that Marconi claimed to have heard the Morse code signal were all in the afternoon, marked by the 2 vertical blue lines. Makes one wonder what Marconi actually heard. This figure illustrates the concept for how one might use WSPR to track an aircraft. A link between a transmitter in Europe and a receiver on Australia could have crossed the flight path of MH370 as it flew south. If MH370 happened to be at the crossing point during a transmission, it might have caused an anomaly in either the signal-to-noise ratio or in the frequency due to the Doppler effect. For links that do not directly cross the path of MH370, one could extend the link along a great circle to the point where the flight path is reached, making these links candidates for showing anomalies as well. The idea for using WSPR to track aircraft was developed by Richard Godfrey into a framework called Global Detection and Tracking of Aircraft Anywhere, Anytime, GDT-AAA. It was first presented May 4, 2021 on his website as indicated. The methodology has changed materially over the years, so what I discuss here is not what was originally presented. The assertion is that the presence of an aircraft can alter the properties of a whisper signal such that they show up as anomalies. These include signal-to-noise ratio, frequency, and frequency drift. I'm unclear if frequency drift is still used, but will include it for completeness. A particular time of interest might be when an aircraft has passed between a transmitter and receiver. For the first two types of anomalies, the procedure is to first select all spots between the transmitter and receiver within plus or minus 3 hours of the time of interest. A minimum of 5 is required. Second, compute the mean and standard deviation of the particular property. Third, an anomaly is a deviation of greater than 0.75 standard deviations, either plus or minus. A drift is any non-zero value. Drift is computed by the whisper decoding software and can be as large as 4 Hz per minute. Two types of geometry are possible. The first has been described as resembling a tripwire, where an aircraft passes between the transmitter and receiver. The second has been described as bistatic radar, where a transmitter sends a signal in the direction of a receiver where it continues along on a great circle path, reflects off an aircraft, and the reflected signal is picked up by the receiver. Variations of that geometry are also possible. In either case, the path between and beyond the transmitter and receiver are computed as exact great circles using a spherical Earth, which are then projected onto the Earth's surface. If an aircraft crosses or passes within 2 kilometers of this path, it is classified as a hit. These principles are illustrated in the example of Turkish Airlines Flight 161 analyzed by Godfrey. On the upper left is a chart showing this flight shortly after takeoff. On the right, the path of this aircraft is shown for 2 minutes starting at 13:52 Universal Time. The extension of the link between W7GW and KV6X intersects the flight path during the time of interest. At the bottom is a table showing data extracted from the Whisper database for 5 spots recorded within 3 hours of either side of the time of interest. The mean and standard deviation for both frequency and signal-noise ratio are computed in the appropriate columns below. The measured frequency and signal-to-noise ratio at the time of interest deviate from the mean by 1.19 and 0.81 standard deviations, respectively. There is also a frequency drift of minus 2 Hz per minute. The physics of the interaction between whisper signals and an aircraft has been described only qualitatively and not always consistently over time. However, the processes are, as best as I understand them, more or less as follows. First, reflection, presumably appropriate for bistatic geometry links. Second, forward scattering, presumably appropriate for tripwire geometry links. The signals are faint. How can this work? Godfrey advances 3 mechanisms. First, coherent integration over 110.6 seconds using FFT software. 2, time on target. An aircraft is illuminated by the whisper signal for 110.6 seconds. 3, aircraft have a large cross-section. This last point can be addressed further. In older texts on radar, the radar cross-section of large jets is often wildly understated. In practice, the cross-section varies quite a bit with illumination and viewing angles, so a single number can be misleading, but might be suitable if one is simply looking for an order of magnitude calculation. Let us look at reflection in more detail. If you had a perfect mirror and you used it to observe an object, then aside from a left-right reversal, you would perceive that object as if there were no mirror at all and at a distance that is the same as the sum of your distance to the mirror and the distance from the mirror to the object. Next, it is necessary to understand a bit of jargon, the definition of a decibel. It is defined to be a ratio of 2 powers, for example, measured in watts. The exact equation is shown. The Whisper database records the signal-to-noise ratio as an integer dB. If one wanted to determine if a particular signal-to-noise ratio were anomalous, the smallest anomaly that could be detected is 1 dB. That is a factor of 1.26. What is the greatest distance for an aircraft to be detected as a 1 dB anomaly? Let us consider the bistatic geometry of a transmitter to receiver to aircraft, perfect reflection, then back to the receiver. Now, something that Godfrey never discusses, although it is implicit in his definition of an anomaly, is that there is a direct signal from the transmitter to the receiver along with the signal reflected back from the aircraft. And it is the sum of those 2 signals that are what are being recorded. Thus, the condition for a 1 dB anomaly is that the combination of the 2 have an excess of 1 dB relative to the direct signal alone. The strength of a signal decreases as the inverse square distance from the transmitter. If reflection off the aircraft were perfect, the strength of the reflected signal would continue to decrease with the distance given by the sum of the transmitter to aircraft plus aircraft to receiver distances. An additional implicit assumption is that the reflector causes the reflected signal to travel in the exact opposite direction of the incoming signal. How an aircraft is supposed to act like such a mirror is beyond the scope of this discussion. There is one extra trick that can be invoked: constructive interference. In this instance, the waves from the direct and reflected signals combine in phase, giving a boost to the detected signal. It is utterly unrealistic to expect it to happen perfectly in practice, but let's just assume it happens anyway. In any case, we find that the maximum distance from the receiver to the aircraft would be 3.4 times the distance from the transmitter to the receiver. This is the optimal case for Godfrey's reflection from a perfect mirror. However, whisper signals are radio waves, so one needs to determine if a process known as diffraction is important. While Godfrey has mentioned diffraction in the past, his description was inaccurate and he never made any quantitative calculations. The way to determine if diffraction is important is to make use of something called the Fresnel number. It is defined by the equation shown here and depends on the size of a reflecting or scattering surface, the wavelength of the radio wave, and the distance from the receiver to the surface. If the Fresnel number is large compared to unity, then geometric optics apply, and the description of a perfect reflector on the previous page might apply. However, if the Fresnel number is small compared to unity, then wave optics apply and diffraction dominates. As an example, consider a whisper signal in the 14 MHz band, the most common frequency in the whisper database, reflecting off the F layer of the ionosphere, which is at an altitude of approximately 250 kilometers. The Fresnel number is over 12,000, so one can treat the ionosphere as a perfect mirror using geometric optics, and indeed that is what is normally done. For reflection or scattering off an aircraft, however, the situation is quite different. The length of a 777 is 64 meters, while the distances at issue are much larger, often of order 10,000 kilometers or more. The Fresnel number in this case is only 2 parts in 10 to the 5, so wave optics applies. Most importantly, a whisper signal that is incident on a perfect mirror will not be reflected unchanged, but rather will create a diverging beam with an opening angle given by the wavelength over the aircraft length. For a wavelength of 20 meters, the opening angle is 18 degrees. No precise alignment of the transmitter-receiver aircraft is needed, and the receiver can be well away from the transmitter-aircraft line and still receive the reflected signal. However, the reflected signal is now diluted by a factor given by the radar cross-section divided by the square of the distance from the aircraft. Even for the most ridiculous values for the radar cross-section of a 777 of 63,000 square meters, requiring that one be facing down on the aircraft from above instead of from the side, the decrease in strength of the signal compared to a perfect mirror is now reduced by 92 decibels. Such a signal is far too weak to be detected by a whisper receiver. Another assumption made by Godfrey is that a radio signal follows a line-of-sight propagation path which he contends is a great circle around a spherical Earth. Why would one make such an assumption? It reminds us of the Dr. Seuss book The Big Brag, where the worm does indeed have a line of sight that is a great circle around the Earth. Amazing! In reality, a whisper signal bounces multiple times between a spheroidal Earth and a distinctly non-spherical ionosphere, and the path is close to being a geodesic on a spheroidal Earth, not a great circle around a spherical Earth. The ionosphere often displays tilts of order a degree or more, and one might be concerned that the path from the transmitter to the aircraft or aircraft to the receiver will have cross-track errors large enough to affect the computation of the crossing point of a link with the path of an aircraft. In various places, Godfrey has asserted that a perfect reflection would be minus 180 degrees, outgoing path is the reverse of the incoming path, and that he finds an average value of minus 180 with a scatter of 0.323 degrees, indicating that short-term disturbances of the ionosphere are ironed out during the integration period. This statement is total balderdash. The links were deliberately cherry-picked to have an alignment of minus 180 degrees as measured on a spherical Earth. The variation of 0.323 degrees is due to the fact that the reverse bearing was computed not using a spherical Earth, but rather a spheroidal Earth with the Vincenti formula. This scatter is a mathematical artifact that has nothing to do with ionospheric tilts. A classic paper by Bramley and Ross from 1951 provides a nice, albeit far from unique, example of the behavior of ionospheric tilts. What they did was to measure the bearing of a signal being broadcast from a station in northern Scotland to a receiver outside London via one-hop ionospheric propagation. The bearing was measured with the directional antenna every 30 seconds. Offsets of 1 to 2 degrees were common, and the coherence timescale was of order 10 minutes or more. The 2-minute length of a whisper reception would not be long enough to iron out these fluctuations. This slide shows an example of cherry-picking in action. Godfrey claims to have detected Qantas Flight 64 on January 26, 2022, while it was over the Indian Ocean as it flew from South Africa to Australia. The figure on the left is his depiction of all the whisper links that he thought were affected by the presence of that aircraft. To the upper right is an image showing the paths of all whisper links in progress during that time. I decided to throw a dart at it, applying the same procedures as were used by Godfrey, and lo, I too was able to detect the dart using whisper. Once again, amazing. Let us return to Turkish Airlines Flight 161 and the link between W7GW and KV6X, which Godfrey claims exhibits a frequency anomaly. I've plotted here a schematic version of a waterfall diagram, once again with frequency increasing horizontally across the figure and time increasing downward. There were 5 spots listed in Godfrey's table, and I have plotted the frequencies of each spot as a function of time. The first 2 spots had the same frequency, but then the frequency jumped around. Why? If you stick to one frequency, you might have collisions with another whisper operator who by chance also selected the same frequency. To mitigate this problem, many whisper operators use software that randomizes the choice of frequency such that the probability of such collisions is reduced. The frequency chosen at 1342 happened to be near the edge of the whisper band. Godfrey decided that such an outlier was not due to a randomizer in the transmitter software, but rather must be an anomaly due to the presence of an aircraft. Once again, amazing. Continuing once again with the Turkish Airlines flight. During the time of the whisper link at 1342, the aircraft was receding from both the transmitter and receiver, meaning that the reflected signal would be Doppler shifted down in frequency by 15 Hz, which is 2.5 times the whisper signal bandwidth. The whisper decoding software would not mix the reflected signal with the direct signal, but rather would decode it separately as a duplicate of the direct signal spot. As noted previously, Godfrey has asserted that whisper software performs coherent integration over 110.6 seconds using FFT software, and that this is one reason why weak signals can be decoded successfully. I decided to download that FFT software, it's a file named whisperd.c, and locate the code where integration was being performed. I inserted some extra print statements and ran the code on a set of raw whisper data files. In short, I found that successful decoding of spots occurred only with n block equals 1. From the comments section of the code, n block equals 1 corresponds to non-coherent detection of individual symbols. In short, no coherent integration of any kind is being performed at all. Up to now, I focused on links with bistatic radar geometry. In a previous publication, I analyzed the performance of links with the tripwire geometry. The bottom line is that the story is the same. Diffraction dilutes any scattered signal to the point of insignificance. Simon Maskell, a professor at the University of Liverpool, has appeared as a co-author on recent reports written by Godfrey. Like Godfrey, he enjoys being in the public spotlight. Here he is pictured appearing on BBC Breakfast in December 2024, explaining how whisper operates like a tripwire when detecting aircraft. What Simon does not seem to be aware of is that in the most recent paper that he had co-authored from February 15, 2024, not a single link had the geometry of a tripwire. Simon, can you explain to the BBC what is going on instead with those links? A question that comes up from time to time is whether any other aircraft are crossing a link at the same time as the targeted aircraft. In a report of January 1, 2025, Godfrey selected a sample of 48 flights of Boeing 777 aircraft at various locations around the globe in order to see if he could track them. Just for fun, I selected one aircraft, QTR 8776, and one link, M0MBO in England to OH6BG in Finland, and decided to check whether any other aircraft were crossing the path of the link at the same time using the methods outlined by Godfrey. I found that there were 14 other such aircraft, including 2 Boeing 777s, 1 Boeing 747, 1 Boeing 787, and 1 Airbus A330, along with a host of narrow-body aircraft such as A320s or Boeing 737s. In another case, I found that a link was being crossed by 46 aircraft at the same time. Such economy of scale in being able to track so many aircraft with a single whisper link. Do whisper signals obey the inverse square law? Here we have plotted the signal-to-noise ratio versus transmitter-receiver distance for all whisper spots, all frequencies in the whisper database for March 7, 2014, the day that MH370 disappeared. It's clear that the signal strength drops with distance. The dark blue circles correspond to what one would expect for an inverse square law, and while it's difficult to say that it matches the data best, there is clearly a trend that signals become weaker with distance. Here is a similar plot in which I show the signal-to-noise ratio and frequency deviations as computed by Godfrey as a function of distance, in this case with distances normalized by the transmitter-receiver distance. The data are from the January 1, 2025 report. The points with error bars give the median and first and third quartiles binned by distance. Tripwire geometry links are all in the leftmost bin. Just like with the signal-to-noise ratio, one would expect the deviations to decrease with increasing distance of the aircraft from the receiver. However, the points show no trend of any sort with distance. Even the tripwire links, where there would be reason to see an enhancement, show no difference either. Godfrey uses something called a receiver operating characteristic curve to demonstrate that WSPR is positively detecting aircraft. Without delving into detail, the ROC compares the true positive rate, i.e. fraction of links that show an anomaly when an aircraft is present, with the false positive rate, i.e. fraction of links that show an anomaly when no aircraft is present. The curve clearly shows an excess of the true positive rate at a level that somewhat exceeds the 2 sigma error bar. However, I am unable to reproduce this figure. Godfrey supplies 2 tables with the paper, one giving information for each aircraft along with the number of true and false positives for each, and a second table with the actual link and spot information. The 2 tables do not agree. From the aircraft table, I find that the true and false positive rates are essentially equal, with 1108 links total. The signal table gives different numbers, with the true positive rate increasing to 72%, while the false positive rate decreases to 65%, and the total number of links decreases to 1078. It appears that the sample times from which the data were drawn are different for the 2 tables. Without knowing how the sample times were chosen, it is not possible to determine if the ROC curve is reliable or yet another example of cherry picking. Finally, how much credibility should be assigned to the WSPR location? First, however, we need to ask which WSPR location. 3 have been reported so far. The first one was presented with tremendous fanfare. Here are some headlines and press reports at the time. 2 new reports verify MH370 location technology. The crash location remains as originally defined at 33 South, 95 East, and is shown to be a sound conclusion. That is the November 30th, 2021 position in the lower left of the figure, and it has long since been abandoned by its proponents. The current WSPR position du jour is the September 21st, 2024 location. Here is a more recent press report. The crash location is 29 South, 99 East. Note that the new location is 335 nautical miles from the first. Why should we trust it any more than the previous 2 failed attempts? So now you know what WSPR can and cannot do. Suppose ChatGPT were to ask you, can WSPR be used to track aircraft? How would you reply?